Look at this processor chip pulsing with binary data. Those ones and zeros are the only language a computer actually understands. Since typing millions of ones and zeros by hand is impossible for us, we use Java. Think of Java as a bridge, a language built with human words that a computer can be taught to read. Today, we are going to write a short piece of code, translate it, and send it across that bridge to make the machine speak. We will do this by writing a Hello World program. It is the classic first step every software developer takes when learning a new language. Writing code is simply learning how to give precise instructions. We write down what we want, and a specific tool translates it for the machine. The first step is to create a blank text file. We will name it main.java. That .java extension at the end is mandatory. It tells the computer that the file contains Java instructions. Here in this animated diagram of a code editor, we are typing out our foundation, public class main. A class is simply a large container that holds all the instructions for our program. Inside that container, we need a starting gate. We add a line that says public static void main. This is the main method, and it acts as the exact front door where the computer will begin reading your instructions. Do not worry about memorizing these specific words right now. The important part to notice is the curly braces. They visually show you the boundaries of the container holding your commands. Now we give the actual instruction. We write system.out.println, followed by hello world inside quotation marks. This explicitly tells the computer to push these human words straight to the screen. Right now, this entire file is still just a human-readable blueprint. If we hand it directly to the computer as it is, the machine won't know what to do with it. To bridge that gap, we open up this command line terminal window. This interface is where we type direct commands to interact with the Java translator. We start by typing javac main.java. That C at the end stands for compiler. This command explicitly summons the tool that will translate our work. This animated diagram shows exactly what the compiler does. It scans your human-readable file and instantly transforms those instructions into a dense, machine-readable format called bytecode. Your code is now fully translated. The machine is holding the bytecode instructions, waiting for the signal to act. To give that signal, we type one final command, java main. This triggers the computer to read the bytecode and execute the program. Immediately, the text "Hello World" appears on the terminal screen. The computer perfectly understood your instructions. This flowchart shows the simple cycle that drives all software. You write the code, you compile it into bytecode, and you run it to see the output. Because computers take everything completely literally, that translation step will fail instantly if our grammar isn't perfect. Look at the red warning highlight in this code editor. We left off the semicolon, which acts like a period to end a thought. Here, we typed a lowercase m instead of a capital M. Java is case-sensitive, making this an entirely unrecognized word. Another common hurdle is typing java main.java to run the original human file, instead of java main to target the translated bytecode. When you see these errors, there is no need to panic. Fixing small typos is an entirely normal part of the daily programming process. Once the typos are fixed, the file compiles without errors, and your exact text prints beautifully to the screen. You have successfully written a blueprint, translated it, and commanded the machine. This is the official start of your programming journey. When you write a program in Java, the goal is to create one set of instructions that functions identically across Windows, macOS, and Linux without changing a single line of code. This process starts in a simple text file. You write your logic using Java syntax and save the document with a .java extension. However, your computer's hardware cannot read this text. A CPU understands binary instructions, not the human-readable words used in a source file. To bridge this gap, your code must undergo a translation. We need a way to turn those written words into a format the machine can eventually process. The Java compiler handles the first translation stage. In your terminal, type javac followed by your file name. The .java extension is vital to identify the source file. The compiler then generates a new .class file containing bytecode, an intermediate language lacking final machine instructions. This bytecode serves as a universal format. Because it isn't tied to the specific architecture of the computer that created it, The program is now portable and ready to be moved to any environment. To turn universal bytecode into an active program, we use the Java Virtual Machine, or JVM. The JVM acts as a localized translator, converting that universal bytecode into the specific machine code required by your current operating system. Now that we have our class file, think about the terminal. What command do we use to tell the JVM to execute it? Use the command java followed by the file name. Hit enter, and the JVM executes the code, showing the output. Note the syntax change. We use Java without the C, omitting the .class extension since the JVM automatically looks for the class file. This two-step process, using the JVM as a platform-specific middleman, is exactly what allows the same bytecode to run as a visible application on any machine. It begins with the human-written .java source code. The Java command compiles that source into universal bytecode stored in a .class file. Finally, the Java command hands that bytecode to the JVM, which translates it for the operating system to produce the final output. To master this workflow, remember the sequence. Write your code, compile with Java to create the class file, and run with the Java command. By internalizing this specific two-step process of compilation and execution, you gain the ability to build software all across the digital world. If you are looking at a screen full of programming code for the first time, it probably looks like an intimidating, chaotic wall of text. But as you can see in this diagram, Java isn't a random collection of words. It actually maps perfectly to an organized architectural floor plan. To build a program that actually works, you have to follow a strict set of structural rules. By keeping everything in its exact place, your work becomes much easier to read, fix, and share with a team of other developers. Understanding this structural blueprint is the first step to building any professional Java application. We start with the absolute outer shell of the program, which we call the class declaration. The class acts as the master blueprint. It tells the computer exactly what this specific file is designed to be. Every single piece of data and every instruction you write must live safely inside this outer container. Without a class declaration, the Java program has no foundation. It's the ground upon which we build everything else. Inside that class, we place the main method, nested right here. Think of it as the front door of your program. When you run the application, this exact location is where it steps inside to begin work. If the class builds the house, the main method is the only way for the computer to get inside and start performing tasks. Notice these curly braces acting as walls to contain our logic into organized rooms. Inside, we put instructions called statements. At the end, a semicolon acts like a period, locking the instruction into place so the computer knows it's finished. The curly braces safely group your instructions together, while the semicolons ensure the computer processes those tasks one finished step at a time. Look at the text in the margins. These are comments written on single or multiple lines. They act as human-readable sticky notes for developers. When the computer runs the program, it completely ignores these notes, as they are just for people. Comments are essential for working on a team, as they explain exactly how your blueprint is meant to work. Let's shift our perspective and look at how this structure actually turns from text on a screen into a running program. First, our source code passes through a translator called a compiler. It turns our words into bytecode, a digital manual the machine can follow. Then the JVM, the Java Virtual Machine, reads that manual and produces the final output. Because this process is handled by a machine, the translator can't guess what you mean if a semicolon or bracket is missing. It needs a perfect blueprint to get the job done. Looking at our assembled program, these lines are no longer a mystery. The class, main method, statements, braces, and semicolons work together to form an organized system. To maintain professional standards, follow simple habits like keeping your code aligned and using descriptive names. Looking at our course map, the foundations of your first Java program are now in place. You've learned how to build the frame of the house. In our next lesson, we'll start filling those rooms with actual data.